I built a job queue project from scratch in Golang, and in this video I'm going to walk you guys through what I built and what I learned while building it. Okay, so one of the first things that stuck out to me was logging and observability. So essentially, I'm just going to start us off with, a code example. So if we navigate to the main application, and I have sort of abstracted away the starting logic of the application in this app package, and we go there. The first thing that I do here is I initialize a logger, which, it's like before I used to kind of just use the log package and I used to just log everything. I didn't even know that you could kind of, have this sort of options where you could, make a log that's like an information where it's going to be logged in that. I think these are called severity levels. I'm not entirely sure, but that's my interpretation of them. But essentially what I do here is I set up the logger. I pass in the option of a JSON handler because I want structured logging. And essentially what this gives me is, as you would assume, structured logging. Well, it's kind of funny because I learned about this, logging and observability from like a course from boot.dev. And in there, they were using all sorts of different options, right? Like there were stack traces, a way to make errors a bit more easy to track. Like there were a bunch of stuff there. But what I did personally, I was like, you know what? It's probably not, my application, it's fine. It doesn't really need all that kind of, that detailed logging to a point where I'm going to have to track every single thing. Because it's like a pretty simple application. It's like a job key. And so I decided that I'm just going to have a simple, a slog logger, and I just kind of learned the logger from boot.dev's course and just used it. It's funny because before I was not really into logging, but now you're going to see, like, if you search logger, there's so many instances in my application where I've used a logger. It's insane. And essentially it just kind of helped me to log certain events, right? It's like I'm not logging at every stage, but I am logging at, after a completion or sometimes the beginning of an event, right? And that certainly helps a lot, both with errors and with debugging. So just like a quick demo, if we go to my worker code, which is essentially the worker, you're going to see that I use the log a lot. And essentially I kind of use dependency injection to provide the logger to whatever place needs it. I'm not sure if it's the best approach, but it's the one that I went with. And in here, you're going to see that I'm essentially attaching a lot of stuff about the logger. So it's like, hey, this is the current job ID. This is the name of the worker, the number of the worker that's executing the job. And that's essentially going to be appended with every log that I make here. And that's really good because you've got more data to work with. And you can kind of see throughout my application, the log, especially structured logging, has been really great. So the second point is using metrics. And this one's, I'll be honest, I did not really see a whole bunch of instant benefit of using this, but I could kind of imagine how if you have a big application with tons of users, that this could be pretty helpful. But for my case, if you go to my metrics file here, this is like a to-do. I wanted to add it for the HTTP layer 2, but I did not. But anyway, you're going to see that I've these kind of metrics, which is like the first one is job processed, which tracks the total number of jobs that have been processed, job fail, job retry, queue depth. And if we navigate back to the worker, you're going to see again that, for instance, here, right over here, I sort of note the start time, which is like, hey, we're starting to process the job now, and I run the job processing, which obviously takes a certain amount of time, and just when that's completed, I calculate the amount of time it took to complete the job, and then I put it in the metric, right, that hey, this is how long it took to complete the job, which I think can be like a great metric, especially in production. But as someone that's building this app to learn, not really that useful for me specifically, to be honest. But yeah. Okay, aside from that, the one place that metrics was really great was there are certain instances. For example, if you come here to the fail job, this little function which essentially marks a job as failed, you're going to see that there are a lot of instances where you're making a DB call or any kind of IO operation where that thing could error out. And I've always been curious that, hey, what if it does? Like, I mean, usually we just kind of return out and continue with our business, but that always felt kind of loose. But I feel like now when you report that crash and you store it in a metric, you have like this sort of data that, hey, this is when it crashed, this is how many times, and you can kind of collect all that stuff and you can work on it, which makes the fear of, you know, your app just suddenly dying a lot more manageable, dare I say. Okay, so the second thing that I learned a lot while I was building this project was graceful shutdown, and more specifically, graceful shutdown for subcomponents where I had to sort of coordinate that, hey, we are shutting you down, you got to shut down, and you've got this amount of time to shut down. And if you can't do that, we're going to do a hard shutdown and we're going to close everything. And essentially, you can see that if you go to my main application here. The first thing I do is I listen for the signal of segint and segterm, which is, you know, like, hey, if you press Control C, or if we're, you know, in Kubernetes or something. I don't actually know how that works, but I do know that it works with Control C. You know, you're going to get a signal, and when I do get the signal, I trigger the app.shutdown, which essentially what this does is, you know, it logs that, you know, it's gotten a shutdown signal, and it starts 2 wait groups, and then it waits for the wait groups to finish. And in those wait groups, the first thing I do is I try to stop the worker pool, which the worker pool is essentially a component that's responsible for controlling and coordinating all the workers. And this is what I was talking about with this project. It's like you've got components that control other components, and essentially that's what worker pool does. And it takes like a duration. It's like, hey, how long have we got to complete the work? Which for this, I've given 20 seconds, which is, you know, plenty of time. And what happens in the stop is we essentially create a timeout with that amount of duration as like a threshold. We create a done channel, and we cancel out the global context, which we had created in here, which essentially is responsible for signaling the worker that, hey, we're done, we got to log out, and we got to close the worker. And the way it does that is if you go to the start function, you're going to notice that we initialize the context, the same p.cancel that we literally canceled the stop function. So what do is we launch a certain amount of workers. We launch them in a wait group, and essentially we have a select statement with a default, so it's non-blocking, and the context is expired. We break outer, which means that we just get out of the loop, right? We don't want to continue. We've done our work, you know, and you're free to go. And essentially we leave and we just log out, worker finished, and that's it. And when we go back to the stop function, after canceling the context, we start another go routine in which we wait for the wait groups that we started as workers to complete. And when they are completed, we close the done channel. And just after that, we have this cool little select done channel pattern where it's like, if we're able to close the done channel before the time threshold, we close gracefully. And if we are not, then we have to do a force shutdown. So that's the shutdown for the worker. And then I also have one for the scheduler. And the scheduler is essentially responsible for adding the dimension of time to our queue. So our queue is just this in-memory it's multiple arrays, but you can kind of think of it like an in-memory storage where we store jobs that are going to be processed. And scheduler is essentially a thing I've created to add the dimension of time. So what I do here is I cancel the context and I wait for the done channel. And it's essentially the same pattern. You go up a little bit and you see that you notice that if the context has been canceled, we just return out. We just like, hey man, scheduler's done. And on the other wait group, we try to shut down the server, and this is actually really interesting because I had to read a blog post about it. So the first thing we do is we create a timeout for that said duration, which I've actually kept at 15 seconds. And what happens here is, we create a context and a deadline for, like, it's not really a deadline context, it's a timeout. But, I like to think of it like a little deadline you got for X amount of, time. And essentially, we try to trigger the shutdown and cancel the context. Now, here we shut down the server. We pass in a context, which essentially tries to, as far as I know, it doesn't take any new requests, but it still processes the ones that it already has. And just after that, we cancel the context. And this is where it gets a little bit interesting, because what I do when I have to initialize the server is I have this context and the cancel function there. I essentially initialize the context, and I set the base context for the HTTP server to the context of the s.context that I just initialized. And the reason I do that is when I cancel the context via s.cancel, what happens in the handler, for instance, if you navigate to the handler, the HTTP handler, is anywhere that we have used r.context, which is essentially every place that does I/O operations, it will sort of cancel this context. So this base context is like a base context for the r.context, which is pretty solid. And what happens here is if we fail to shut down in 15 minutes, we have this shutdown hard period for like 3 seconds, which is like, hey, all the handlers that are still working, you've got like 3 seconds to wrap up. And if they fail at that, then we just return out, right? It's like the shutdown failed. Well, technically, we're still going to say graceful shutdown, but it was a hard shutdown. Okay, now moving on to the third point, which is race conditions. Now, this one's really interesting because there were a lot of race conditions, like a lot. In the worker, in the queue, in the scheduler, in the handler even. Any place that I needed to guard the shared data, there were potential races. But the one that stuck out to me the most was the one that happened in the scheduler. So if you go to the scheduler, and essentially, I'm just going to give a quick walkthrough. What happens is I've got the schedule job function, which takes a job ID. It takes a schedule time, which is like, hey, when do you want to schedule the job? And it takes a priority level, which is like, hey, is it high priority, low, or normal, right? And it essentially is like it's like a slice or array, whatever way you want to look at it, which essentially adds the element and then sorts it by the earliest time. So the time that's like the earliest is going to be at the top. A heap would have technically been better here. I'm pretty sure it would have, but I didn't really, mind that. Due to it being a really small in-memory data structure, it really doesn't matter in this scenario. So I used an slice and kind of just sorted it. Probably a heap would have been better. Now, what I do here after appending it to the slice is I send a wake-up signal, which is received in the manage schedule go routine, and I run this as like a go routine when I edit the scheduler. And what this does is it tries to read whether the list is empty or not, and if it's now, then it creates it stores the job as like a pointer, because if you haven't noticed, the jobs that we're storing, we're actually storing a pointer to that struct, which is the job. We're not directly storing the value, and there's a reason for that, which is a race condition. I'll get to that in a second. Essentially, we just add the job and like the timer. We turn on the timer, and we put the channel here, and then we unlock, and then we wait on the select statement. And what happens here is if we get a cancel context signal, we get out. If we get a new wake-up signal that's like, hey, a new item has been appended, we continue. And we continue because, there is a chance that the timer that just got added could be earlier than the one that we currently have, and that's why we continue. I'm pretty sure there's probably a better way to do this, but that's what I did, you know. And the last thing is when we actually have an expired timer, and if remove scheduled job returns a falsely value, we just continue, or else we enqueue the job. So the entire magic of this race condition is in the remove schedule job, because if you look at it, we acquire the lock, we unlock it, we leap through the array, and we see if there's any pointer that matches the one that we currently have stored as the current job. And if there is, we essentially cut it out of the slice, and we set its index to nil, you know, to kind of help out the, I don't know, I wouldn't use the word help, but like, you know, let the garbage collector know that, hey, you gotta take care of this value. And then we shrink the length, and we return true, or else we return false if it doesn't exist. Now here's the whole thing here. The whole point is, if we know that our slice is sorted by the job that's at the earliest is going to be the job that's going to be executed and should be enqueued the first. But the problem here is that there is a chance, it's a very small window, but it is possible, as when you try to acquire the lock in the remove schedule job, a new job could be added in that array, and that job could be even earlier than the one that's currently at the top. And that's the whole thing. And if that were to happen, we would essentially eliminate a different job from the scheduler, and that's just not what we want. That's really bad. So yeah, that was the race condition, and I solved it via using pointers. So there's that. Alright, so the fourth thing that I want to talk about is in-memory queues. And I've got two subpoints here. The first is a priority queue, which has starvation, and the second is a relation between the queue and the worker. Okay, so the queue. What is the queue? So in my current app, I have this file called the queue.go, and this is literally the queue. That's it. It's just a single file that contains the code for the queue. And I'm not going to talk about all the lines of code here, but essentially what we do here, I'm going to explain that. Oh God, where is the type? Yeah, here it is. Yeah, the queue. So we have priority queues as like a field, which is essentially, if you go at it, it's like a struct with three separate queues: high, normal, and low. And that is how I represent priority queues. And just below that, we've got a notify channel, and then there's a locker, there's a mutex, and then there's queue size per priority, which essentially stores how many current jobs are there in each queues, which I use for maintaining a limit for the queue. You know, like you shouldn't pass a certain amount of jobs. That about it. Okay, so this is the main design of our queue, which is the in-queue job function. And what this does is it takes the job ID, the priority level, and a force boolean. Now I'll just go through the force boolean. If the force boolean is true, we do not verify it against the capacity. And the reason I've enabled this as an option is because I have a function called recover job, which essentially runs at the start. And the whole purpose of this function is to sort of recover the jobs that were lost. It just kind of re-queues them back. And we do not want any kind of trouble with capacity at that moment. All we want to do is re-queue the jobs. And that is precisely why I have the force boolean. We check the capacity, which is another, one of the little helper functions, which essentially sees if the priority is valid or not. And it just kind of has like a switch statement for each of the three priorities. It just kind of maps it. And if it's greater than the said limit, we return an error. That's about it. And if you go back to the check capacity, in queue job, after verifying that, hey, this is a capacity, what we do after that is we acquire the loss and we re-verify that. The reason we re-verify is to avoid a race condition. That's about it. And then we, switch over the queue priority again, and if it's a high queue, we append it to the high list. If it's a normal, And then we do the following. And then what we do is we use our size per priority little slice that we have, and we index it via the queue priority, which essentially is like a switch statement, and we just append 1. That's about it, nothing more. And besides that, we increment the queue depth as like a metric, and then we send the notified signal. So essentially the whole point of the enqueue job is to enqueue the job, see if there's any space, and if there is, enqueue it. If there's not, return an error. So yeah, that's our entire enqueue job implementation. It just essentially checks that. Now we go to the relationship of queue with the worker. So if you go to get work and you kind of reference it, well, I've got a lot of functions here, but if you go to worker.go, so what we do in the do work function, which is like a function from the worker, is we try to get work via this sort of function that queue provides. And what this does is it has an infinite loop. And the first thing it has is a select statement, which is like, hey, if the context has been canceled, get out, no work, which, okay. And essentially what it does after that is it acquires a lock, it tries to get a queue, and if it fails, it unlocks, and it waits on a channel, like a notify that, hey, we've got more information, or it just, waits on the context cancellation. And if we do have some value, so the queue is not empty, what we do is we take out the first element. And you're going to see just like a weird syntax here, but it's essentially because select queue, this function, and that's what we're going to talk about now, it essentially returns the pointer of the queue that it needs to return. So for instance, if a worker is making a request and it needs a job, it's always going to return from the higher priorities before it gets to the lower ones. And that kind of causes starvation in a way that if you've got a few normal jobs, but you've got a lot of high jobs, the normal jobs are literally never going to get taken insofar as the high jobs are not empty. And that can be a design problem. For me, it was not. My whole idea is, hey, a high priority is a high priority period, but there's that. And essentially, we get the job, we slice the list, change the size, and we do the metrics, and that's about it. And yeah, and if you go to the worker for a second, what you're going to notice here is if the get work fails, if it errors out, the only way it can error out is if our context has been canceled, in which case we return out, which again supports our shutdown signal. Okay, so we're back to the final thing, and probably one of the most important one for this whole application, which is generic worker implementation. So if you're going to notice, well, you're probably not, because I didn't really show the worker code that much, but essentially, our worker, if you go to the manage job processing function, which is essentially a little function that takes into context and has like a built-in recovery because, managing job processing could potentially fail. It first validates the job payload, which I'll get to in a second. Then it calls the timeout, and then it tries to call the handler.process on the job handler that it got. So the way it works, if we go to our handler, not the handler, but like the HTTP handler. So the first thing we do in the create job function is we have to try to read the JSON, but the way we kind of have like the payload, not like the actual payload, but the payload of the struct, is we take a job type, we take a payload, and we take a priority of the job. Obviously, it's not a good design. You don't want to be allowing the user to fill in the priority, but I did not really think about putting in authentication. It was not a priority here. Okay, so job type is essentially a string, which is like, hey, what kind of job is it, and does our system even supports that? Okay. And so what we do is we try to read the JSON in this request variable, and if it's successful, we try to get the handler, which essentially the get job handler function. What it does is it takes a job type, which is like a string, obviously, and it looks through in this hash map, and if there exists a handler, it returns that. If not, it returns an error. And what this helps us with is, hey, is this like a valid job that our system can even process? And essentially the way we register handlers is, sorry, if you go to handler.go, right, here, what we do is, in order for there to be a specific job handler, you only need two functions. The first is validate. It's like, hey, is this payload valid or not? And the second is process, which is like, hey, you actually got to process the job and do the little work. So for instance, if we go to our handler and we go to, let's say, the image handler, the first thing we do here is we create a struct, right? Image handler, it's like a little struct, which is going to have the methods that are going to implement the handler there. And we provide just give me a second, where is it? Yeah, we provide a validate function exactly of the signature that was created in that interface. And we do the same with the process function, and that's about it. That's kind of how we implement handlers, and then we have this register variable, which stores like a hash map, and we add our available handlers here. And I think it's pretty cool because when you look at it, because before I kind of had this single image handler sort of job queue, which the only thing my job queue could do was handle images, and I was like, well, that's not great. So I sort of created this functionality to handle generic jobs, and that's how it works. And you can see that again here. It tries to validate. If the validation fails, it returns an error, and just goes through stuff. And yeah, that's about it. And the last thing I'll show you about this generic implementation is if you go to the do work, which is like the main thing of the work here, is you go down a little bit, and again, we use the same function to get the handler to kind of know, hey, is it a valid handler? And if it's not, we error out, and then we sort of try to manage the job processing, which in turn also revalidates the payload, because hey, we do not want bad payload here. And okay, so essentially what I learned from this section is how do you like sort of create stuff that's able to support more generic dare I say processes, right? Because it was really hard for me to sort of reason through, hey, how the hell am I going to add so many like ways that I can process a job? But turns out it's very simple. You just got this interface that you have to implement a few functions, and boom, you've got a generic job queue. Alright guys, that's about it for today. It's a pretty long video, and it's actually one of my first that I'm recording where I'm actually talking about the things I'm building, so let's just see how it goes. So yeah, I hope you guys liked the video, and make sure to share some feedback if you've got any opinions, and yeah, hope you have a great day.